Hello, statistics scholars. Dr. McNeil here. Congratulations on reaching the end of the semester. As you look back, I am sure you feel as if I do. There were lots of moments where it would have been easy to be overwhelmed or to feel stuck or to actually even sort of be a little bit disinterested in all of the terms and concepts and formulas that you've learned, but you stuck it out. And here we are at the final week. Next week is the final exam. I'm looking forward to that. I'm sure you are, as you prepare for the winter holiday break. So I thought this would be a great opportunity to clarify by giving one final lecture on probably one of the most challenging, maybe even a little frustrating if you've been following along in the textbook, statistical concepts or inferential statistical formulas that we're going to tackle now, called linear regression. So for this lesson, you really do need your thinking cap. Put it on either physically or metaphysically. I hope that the process that I've invited you to join me in learning rituals of putting on a thinking cap really has helped you survive some of the challenges that you've encountered in this semester. Research says that learning rituals like a thinking cap help you move your brain from stress to rest, and then because it's much more difficult to learn something new or challenging when your brain is stressful. And so just the act of sort of transitioning by putting on a thinking cap transitions your mind from a stressful response to a restful response. And that's exactly what you're going to need to take on this challenge. But let's take a look at a way that I'd like you to begin to think about linear regression. So let's start here. What is this? Take a look. And now this. What do you see here? What's the connection between the first thing and the second thing? And now take a look here. And one more. Take a look here. What you see are various models. We have a model plane, a model truck, a model home, and a runway model. I'm using these images as an example very specifically to illustrate that linear regression really is linear prediction, but it's prediction based on a model. And just like a truck, plane, house, model, runway model, it is meant to be, models are not the thing. A model plane is not a real plane, a model truck is not a real truck, a house is not the real house, and models don't represent all bodies. So the model represents the thing, it's not the thing itself. And so linear regression is a way of modeling what's happening in the population. Another way to look at it might be useful this way. Here we have sort of that vending machine. This is a really good example of what I'm talking about, where with the vending machine, you press in exactly what you want. You press A1 and you get the A1 snack, A2, A3, A4, like that. So linear regression is a way of being able to predict based on one activity what's going to happen in another activity. It really builds on everything that we've looked at for the last 2 weeks. It builds on ANOVAs and correlation. But let's take a look at the textbook, chapter 13. And here we arrived at the 13th chapter. Unfortunately, we won't get to do the last inferential test in the textbook called chi-square, but we've covered quite a lot of ground. Let's zero in on the vocabulary that is probably the most relevant to my overview lecture. All right, let's take a look at a few things. I want to first take a look at line of best fit. That's really what a linear regression is. It is a line of best fit in or on a scatter plot. It sort of splits the dots, the plots in half, so that half of the plots are sort of above it and half of the are sort of below it. You can think of the line of best fit like the central tendency or the mean. How the mean is in the middle, it represents the data set, but it doesn't touch all of the data, but it stands in for the data. The line of best fit, it doesn't touch every dot, but it is meant to express the relationship of all the dots. It's supposed to sort of be the representative of all the dots, and I think you're going to see that in a second. Let's also talk about, residual and error. Statistics is the study of language. I've said that many times throughout the semester. And sometimes it's important to remember that the language that statistics uses is not often the language or the definition or the meaning that we think about in everyday life. And residual and error are that kind of example. Residual and error essentially mean the same thing, but what they mean is the disparity between what we predicted and what we observed. So it's the inefficiency of the model to predict the outcome. And I'll explain that a little bit more. And let's stop there, and I'll let you discover some of the other vocabulary or keywords. Let's jump into how this works. I'm going to go through the example in the textbook, and I'm even going to go to the mat to show you a little bit how this works in real time. I'm especially doing this because there's some errors in the textbook. And so if you attempted to tackle this on your own and you found the error, maybe you got a little bit frustrated because it seemed that the book let you down. So I'm here to address that. So again, as I said, the line of best fit is a way of representing all of the dots in the scatter plot. It represents every point, even though it may not touch every point, it may not even touch any points, but it's essentially the central tendency of the dots. One other way of thinking about it is that it's a formalized way of calculating where that line is and how that line is drawn. And you're going to see that in a second. Again, even though the term is linear regression, and in class this week, we talked about how linear regression sounds like something's wrong, it sounds like something is going backwards, and indeed it really is. It's really how the line regresses back to the mean. But for practical purposes, I'd like you to think of linear regression as more like linear prediction, that we're going to predict the outcome of X to Y in a straight line using a sample. So I'm going to introduce a new term. I'll write it here and you'll see it because the new terms have new definitions, new formulas, and some new meanings. So let's start with y hat. Y hat is a variable. It really means the predicted y. And the formula for y hat is a plus bx. All right, that's the formula. We'll talk about that in a second. It's the predicted value of y for a particular x. A is the intercept line. It's where the line starts, where it intercepts. Another way of thinking of A is the value of y when x is 0. I'll say it again. The intercept is where the line starts, where it comes into the scatter plot. Another way of thinking of the intercept is A is the value of y when x is 0. And there's a formula for that as well. B, or beta, that's the Greek letter, is the slope of the line, the exchange. There's an exchange rate that every time x moves 1 unit, B describes the interchange of movement, or the exchange of movement, to y. And x is just the value of the observed x that we found. And I'll explain a little bit more about that, but here I'll start to build the formula. I suggest that you sort of work along with me. I just wrote down the formula for y hat. Okay, see, what you're looking at right now is an x and y plot. There we go. Okay, here is the x axis and here's the y axis. You can see the dots, or the plots, are where x and y intersect. So if this is, let's say this one is about, that's 3 on the x-axis, and let's say about 61 on the y-axis. Let's move down a little bit further. Let's say this is about 15 on the x-axis and about 68 on the y-axis. So you can see that every dot has an x and y coordinate. And now you see the line of best fit. That's this red line here. The red line is the model's prediction of where y should be along every value of x that you see. So you can see that this line is, in other words, this line is saying this is what we think, statistics. This is what statistics thinks, or the model thinks, that every dot should be along this line. And of course, every dot is not along this line. There are some dots that are on the line, and there are some dots that are very close to the line. And in those cases, the line is the model is very effective and efficient in predicting what y should be given the x. But where there is a lot of space, meaning here it's quite a bit above the line, here the model expects y to be here, but it's way up here. So in other words, this is an ineffective or an efficient way that the model has been, it's not very efficient or effective in predicting the y. And so this would be considered a residual or an error. So if there are more errors than residual, then the line isn't very effective. But if there is more, if it's closer to the, what did I say? If there's more residual, so let me fix that. If there's no more residual and error than meeting along the line, then the line isn't very efficient. But if much of, or a significant amount of the data hovers around the line, then the line is very efficient in predicting x and y. And you'll see that in action in a second. Okay, so this looks like the ANOVA table that you've seen before. In fact, it is the ANOVA table. The only difference is in the ANOVA table, we see sum of squares between and sum of squares within and total here. But for linear regression, we see model, which is what the line is attempting to do, and error, which are those spaces above or below the line. Here's the formula for the model and the formula for the error. In essence, the formula for the model, what the model is predicting, is the sum of every predicted y. So if we have 18 in our data set, in fact we do, I'm going to write that down, n is 18. That would be 18 predicted y's from every one of the 18 x's that we have, minus the mean of y squared. That's what the model is. In other words, is how far are the predicted y's from the mean of y squared. If we take a look at the formula for the error, is the sum of all the y's, every y that we observed, minus the y that we predicted, or in other words, the errors, or just the, hopefully it's not errors, squared. And then the total is the sum of the model and the error. Now take a look here. This looks a lot like the ANOVA degrees of freedom, except when we're using the ANOVA table for linear regression. The degrees of freedom for the model, if we're doing a simple linear regression, meaning only one predictor variable, or 1x, then the degrees of freedom is always 1. For the error degrees of freedom, however, it's just n minus 2. And so I'm going to write that down. Our degrees of freedom, the numerator is always 1, and the denominator is n minus 2. In our case, since we have 18, it's 18 minus 2, or 16. So we use the exact same F chart that we use in ANOVA to find the critical value for 1 as the numerator and 16 as the denominator. Let's go check that out. Okay, so here we have an excerpt of the F chart. So we're looking for 1 in the numerator and 16 for the denominator. So that makes the critical value for this data set is 4.49. I just wrote that down. So let's keep that a little bit in mind. All right, now let's take a look at the data itself. Here is the data, and the data looks like what you've used before in correlations, because we have two variables, an x and a y. So the x variable is the independent variable. Another way of saying that is it's the predictor variable. It's the variable that we're using to predict what y should be. And y is the dependent variable, the variable that measures the outcome of what we do with the independent variable. So we actually call that the outcome variable. All right, then we have, as I said, the y hat. Let's write that here, and you'll see that all when I jump to the map, is the predicted outcome. So we have our observed x, which is the independent variable. We have our observed y, which is the dependent variable, the outcome. And then we have a y that's not on this chart, the y that we're going to predict that it should be based on the model. And then we have, this is the expanded sum of squares table. We have the absolute deviations. When we add them all up, they equal 0. We have the squared deviations, and we add those all up. That equals the sum of squares of x, and that handles x here, those 3 columns. Then we have y, the dependent variable, or the outcome variable. We add them all up. There's the sum of y, there's the sum of x. We need that for a little bit later. Here is the here are the absolute deviations again. When we add those all up, it equals 0. Here are the squared deviations of y. When we add that all up, that's the sum of squares of y. Then we have the products where we multiply the absolute deviation of each x and y to get the result here, or the product here. And then we add them all up, and that's called the sum of products. Okay, while we're here, we need some values. And some of the values are here directly, and some of the values we need to perhaps calculate. So one value that we need to calculate, or two values that we need to calculate, are the values of the mean of x and the mean of y. So if this is the sum of x, then all we have to do is divide that by n. And the sum of x is 356.02, and the n is 18. So I'm going to just do this. You'll see this on, you can work this on your own. We'll jump to the mat in a second. Okay, that equals 19.778. So we can round it up to 19.78. And the mean of y, the sum of y is 314.18. Divide that by 18. That equals 17.454, or 17.45, right? We need the sum of squares of x, and we have that right here, 76.14. And we need the sum of products. Sum of product is 58.29. So I have all of these elements sort of in hand, and we can work through the formulas, which you're going to see in just a second. But here is the line. Here is the line of the data that we are going to be working with. I want to just pause here and show it to you. But in essence, actually, we're going to jump to the mat. I'm going to come back to this, and we'll talk about what is happening here. All right, let's talk about what's really happening in the textbook. I love the textbook because it has great examples. I love it because it's a free textbook, but it's not a perfect textbook. In fact, there are 2 errors that I found in the textbook, and those 2 errors might be significant enough to sort of trip you up. But what I do, so I'm going to point out the error, and we're going to work around it. But I want to talk about the example, or work through the example in the textbook. I love this example because I think it really helps to clarify what we're doing when we're calculating these sort of abstract data sets. We're really trying to answer a very specific question. So let's take a look and see what question the researchers might be trying to answer with this scenario. So if you look, you'll find this in the textbook on page 204. It's talking about happiness and well-being. It says researchers are interested in explaining differences in how happy people are based on how healthy people are. So the connection between happiness and health. They gather data on each of these variables, so x and y, from 18 people and fit a linear regression model to explain the variance. We're going to use the same 4-step hypothesis testing procedure to see if there is a relationship. All right, so I just wanted to sort of position you here to follow along. We're going to work through the same sort of 4-step process and introduce some new symbols, some new formulas. We're going to jump back and work through actually, if we just stay here, work through the ANOVAs and make an answer to the question. All right, so let's jump over to the map. So let's start off with what I said was going on first. As I said that I was going to write the formula for y hat, which is y hat equals a plus b x. A is the intercept, it's where the line comes in. A is the value of y when x is 0. That'll be clear in a second. Plus b, which is the slope or the exchange. In other words, every time y moves something, a explains how much every time x moves one space or one unit, a is what describes how y moves, and that could be any number, positive or negative. And then we have x, and that's just every value of x that we have, or any value of x that we have. And when you see two variables next to each other like this, it may not immediately be clear, but all you're doing is multiplying this by this. So multiplying b and x, and taking that product and adding it to a. And that is the predicted y for whichever x is there. I said that the n was 18. We found our degrees of freedom 1, because 1 is always for a linear regression model, or a simple linear regression, and 16 is the denominator, or n minus 2, so that's 18 minus 2, or 16. And if you recall, I used 1 and 16, the numerator and the denominator, from the F chart to get the critical value of 4.49. We talked about how every x variable is the independent variable, or the predictor. We talked about how every y is the dependent variable, or the outcome of the data that we've collected or observed. Then we have a y hat, which is what we predict the y to be, which may or may not be close or be the y that we observed at all. We used the extended sum of squares chart to get the mean of x. The sum of x was 356.02 divided by 18, which is 19.78. The mean of y, we used the sum of y, which is 314.18, divided that by 18, or n, and we got 17.45. So we know what the means of y and x are. We also just lifted the sum of squares of x from the chart and the sum of products. So we have those values. Okay, let's sort of work through. You can follow along on page 204. Let's see what the researchers are really trying to do. What they're really doing, they're trying to answer this research question. What is the connection between health and happiness? We may assume that there's a connection, may very well be a connection, but we're asking what is the connection by collecting data from these 18 people. So again, we got data from 18 people on X, which is healthy, how healthy they are, and Y, happiness, how happy they are. So somehow we asked them, got a healthy number, and then we got a happiness number. All right, so let's work through the 3 steps. The first step, the null hypothesis, is there is no explanatory relationship between health and happiness. Just like every other null hypothesis we've written. And how we express that is with the beta character. Beta equals 0. beta represents the slope. So the two elements that we're trying to test from the parameter, from the population, are the slope, the exchange of x and y, and the intercept, where the line starts. In other words, what the value of y is when x is 0. So now we're looking for our alternative hypothesis, is that there is an explanatory relationship. Between health and happiness. And we're going to use beta is not equal to 0. So it could be either a positive relationship, explanatory relationship, or a negative. That's what we're testing to find out. Okay. The second thing, or the second step, is what the critical value is. We'd already figured that out from the ANOVA table, the degrees of freedom, 1 and 16, and that got us 4, 4, 9. So in other words, if our result, or the F statistic, is greater than 4, 4, 9, we're going to reject the null hypothesis. All right, so we need some formulas. We need to calculate some formulas, and here are the formulas. We need to calculate the slope, and the formula for the slope is sum of products divided by sum of squares of x. We have those values. We can just go get them. We are also going to figure out the intercept line. The formula for the intercept line is the mean of y minus the slope times the mean of x. We're just going to figure out the slope and multiply that by the mean of x and subtract that from the mean of y. And that is the value of a, or the value of the intercept, which is what x is, the value of x, that value of y when x is 0. And now we need, I'll just write it again, our prediction of y hat. The formula for that is a plus bx. What we're going to do here is calculate this twice. We want to use this for the lowest x value, and we're going to do this again for the highest x value. Okay, so sum of squares is 58.9. Right? Or sorry, sum of products, sorry. Sum of products is 58.9. 0.29. Don't have my glasses on. Divided by the sum of squares of x, and that is 76.14. So we just calculate that. It's pretty easy, right? 58.29 divided by 77.14. And the product, or the quotient of that, the result of 76.14. Yeah, let's try that again. 58.29 divided by 76.14. Okay, we got 0.765 or 0.77, 0.77. So this result means every time x moves 1 unit, y moves positively 0.77 units, right? So almost 3/4 of a unit, a little over 3/4 of a unit. So that's what the slope is. Now let's figure out what the intercept is, because now we know what b is. We know what the slope is. The mean of y is 17.45 minus the slope I'm going to put this in parentheses because we're going to multiply that, times the mean of x, which is 19.78. So when we resolve that, multiply this, and we can do this all in one step with the calculator. 17.45 minus, and then I'm going to open the parentheses, 0.77 times 19.78. Close the parentheses. So we get 2. Somehow that seems wrong. 17.45. Huh. Okay. This is where the textbook made the error. So if we multiply 0.77 times 19.78. I think I might have screwed this up somehow. I love when that happens. So let's see. The mean of y of x, 356.02, divided by 18. Yep, 1978. 314. 18. 18. 17.45. Okay, that's right. The mean of y, 77. Okay. All right. Well, everything seems to be in place. Let's do that again. 0.77 times 19.78. Okay, there we go. I'm not sure, maybe I keyed it in wrong. But in the textbook, you'll see on page 206, you'll see that what I got here is 15.23. I'm going to pop over to the textbook so you can see that this is where the error was. It has the error as, or 77.77 times 19.78. It has the result as 15.03, and I have the result as 15.23. So that's an error. So we get a different number here for the slope, but we're going to go ahead and use the number that they use so that we can see how everything flows from here. I know how disconcerting that can be because you trust the textbook to be correct. This is probably just a rounding error, but everything else actually works just fine. Let's head back over to the mat and work through the problem. So I'm going to say that we're going to use the result that the textbook gave us, which is 2.42. So in other words, 2.42 is the value of y when x is 0. If x is 0, y is 2.42. All right, so now we have that information, and we're going to use the calculation to calculate the predicted y for the smallest x and the largest x, and you'll see why that is in a second. The smallest x, if you look on page, jump back over there so you can see. I want you to feel really comfortable, especially since we had that little snafu with the calculation. The smallest x is right here, 16.99. We're going to see what the y should be if using the model. And that may be very different than the y that we have. Now let's see. The largest x is 23.65. So we're going to predict what y should be if x is 23.65. And it may not be at all the y that we got. All right. So let's do the lowest one. I'll do it here. So A is 2.42 plus B, which is 0.77. We're going to use the lowest x of 16.99, see what that is. And let's go ahead and write it out for the largest one, which is 2.42 plus, again, 0.77. but the largest x was 23.65, I believe, yeah. So now we're going to figure out what the y, predict what the y should be given this x. And that will make sense in just a second. So 2.42 plus, and then parentheses, 0.77 times 16.99. Okay. And that equals 15.50. All right, and I can go ahead and just type over and put, it's the same formula. I'm just going to put 23.65, which is the largest x. We get 20.63. All right, so 15.5 is where the line of best fit starts for y, and 20.63 is where it ends for y. And that makes sense when you look at this chart. This is about 15.5 where the line starts, and where the line ends is 20.6. So that is our line of best fit. And you can see that it's strategically placed so that it is the least distance, that it minimizes the distance of all of the dots from the line. So it's kind of splitting the dots in half. So we've figured out that much so far. And now to figure out the rest, which is, is the model useful in predicting y? In other words, is our f obtained more extreme than our critical value? And to do that, we fill out the ANOVA table. This is the end of the semester. It's not required. No, we're not going to require you to calculate the formula for the model and the error. You could. It's just tedious. I showed it to you earlier. We're just going to give you the values of the model and the error. So as we did that here. And we're going to give you the degrees of freedom. I've just told you that. In fact, we used the degrees of freedom on 1 and 16 to get the critical value of 4.49. And then all we have to then do is create the total by adding the model and the error up, and that gives us the total. Do the same thing here for the degrees of freedom. And then to create the mean square for the model, or the sum of squares for the model and the sum of squares for the error, we just simply divide sum of squares for the model by degrees of freedom, or 44.62 divided by 1, which gives us 44.62. And then we do the same thing, divide the error by the degrees of freedom, that gets us 8.09. And then we divide the mean of square model or the sum of square model from the sum of square error, and that gives us the f obtained. And since 5.52 is higher than 4.49, we're going to reject the null hypothesis. I'm going to go ahead and do that. But now we have one last step to do, which is to decide or evaluate what is the effect size. And this is just like eta squared and ANOVA, except we're using the sum of squares model divided by the sum of squares total. You can get those totals, those values right here. 44.62 divided by 173.99, and that gets us 0.26. In other words, we are explaining 26% of the variance in happiness is based on health. So we're using the same scale, 0.01, 0.09, 0.25 for small, moderate, and large. So 0.26 is a large effect. So then we write out the results. And here's where I want to point out the last mistake. It says the R2, which is the effect size, is less than 0.26. It actually should say equal 0.26. So we would write out the result. based on our sample of 18 people, we can predict levels of happiness based on how healthy someone is. And the effect size was large. We report the F statistic F1 or 1 in 16 equals 5.52, which is what we got. The probability is less than 0.05 and R squared is equal to 0.26. All right, that should do it. With a little practice and some patience with yourself, particularly given that the textbook was incorrect, you'll see that linear regression isn't very, very difficult. A quick recap. We started by putting all the pieces together, knowing what the formula for y hat is, intercept plus slope times x. We knew what our n size was. We used the ANOVA table to get the numerator and the denominator for the degrees of freedom. It's always 1 for a simple linear regression for the degrees of freedom for the numerator. And the denominator is n minus 2. So since we had 18, it's 18 minus 2 or 16. We used 1 in 16 in the F table to get the critical value of 4.49. We remind ourselves that x, the x variable, is the independent variable. In this case, it was health. And the y variable is the outcome variable, predictor and outcome, which happens to be happiness. And we use the linear aspect of linear regression to show where we expect, based on the model, where we expect the y to be, and it may be different than what we observe. And if there is a difference in what we observe versus what the model predicts, that difference is described as residual or error, either above the line or below the line. The line describes where the model expects every y to be. We get the mean of x, we get the mean of y. We did that very simply, although I had a little problem. I want to make sure. Sometimes that happens. We just picked up the sum of squares of x and the sum of product, set that aside, got grounded in what the research question is what is the connection between health and happiness? Realizing that we collected data from 18 people, we collected 18 healthy and 18 happiness responses, the pair of responses from 18 people. We wrote out our null hypothesis that there is no explanatory relationship between health and happiness, and we write it out mathematically as beta equals 0. We rejected the null hypothesis. Then we have the alternative hypothesis that there is an explanatory relationship between health and happiness, and because we don't know if it's a negative or positive explanatory relationship, we say beta is not equal to 0, so we find either side. And by the way, again, we didn't talk about the alpha level, but for ANOVAs and for ANOVA and linear regression, we really only see an alpha of 0.05 because we're looking at 2, and in the case of ANOVA, 3 or more groups or samples. We set aside our critical value. We found it from 1 in 16. It's 4.49. We figure out the slope, the exchange of y to x, and that formula is the sum of product divided by the sum of squares of x. That gave us 0.77, which means every time x moves 1 unit, y moves 0.77 of a unit. We figure out what the intercept is, where the line starts, in other words, what the value of y is when x is 0. That formula is the mean of y minus the slope, which we just figured out, times the mean of x. And we found that in the textbook there was an error in this result, and they gave us 2.42 as the intercept, which we're just going to use because everything else works fine. And then we use the y hat prediction to see where the line starts. and where it ends. And it starts with the lowest x value and the highest x value. We found that the lowest x value was 16.99, the highest x value was 23.65, and we used the y-hat formula to figure it out. 2.42 plus 0.77 times 16.99 gave us 15.50. Did the same thing for the highest value, 2.42, or the intercept, plus 0.77 times 23.65. Remember to make sure you put parentheses if you're doing this all in one fell swoop. They gave us 20.63. That helped us see where the line of best fit actually started and ended. It is, as I said, the formalized position of the line. Then we finished the ANOVA table. I'm not going to show it to you again. You've seen it. It's on pages 207 and 209. They gave us the model and the error. We know what the degrees of freedom are. We figured out the mean squares, and we divided the mean square, the sum of square model, from the sum of square error to get the F obtained, which happened to be 5.52, which is greater than our critical value. Then we figure out the R squared, or the effect size, by dividing the sum of squares model by the sum of squares total. We got 0.26, which means 26% of the variance in happiness can be explained by health, which is a large effect. So again, linear regressions are not hard. They're just a prediction, a model that helps us describe a particular data set. All right, having said that, I hope you have a great rest of the week. I hope this lecture was useful, and I'm looking forward to completing the semester with you with our final exam. And again, really congratulations. Good work.